Today I'm going to take you through some of the history that's taken place over several years and has resulted in what we'll be discussing today. So as we get started, in order to better understand how we got to where we are today, we kind of have to go back a few years. Our testing and study started out with a partnership with the Structural Engineers Association of Northern California, or SEONC, as did an earlier sill bolt anchorage project we collaborated on. As some may know, the 2000 IBC introduced the current method of calculating concrete breakout known as CCD, or the concrete capacity design. And that was incorporated in California in the 07 California Building Code and adopted in the 06 IBC. From there, people started seeing the reality of the impact of these provisions, specifically as it was related to sill bolts and light frame construction. The design capacities for those conditions were so low based on the design equations that the number of bolts that were required to be placed from standard shear wall began to feel excessive. And so we were approached by SEONC and we began to work with them on testing sill bolts and concrete to reestablish the values. This led to code changes into essentially the code that we have today. So moving forward into 2011 and 2012, we're starting to look at a different problem associated with structures that were built for basically for densely populated urban areas. These structures were typically 3, 4, or 5 stories of wood light frame construction over relatively thin concrete elevated podium slabs. Here's a rendering of what one of those structures might look like. And these structures were typically framed with wood shear walls, and they see high overturning demand loads. Now, we saw a lot of typical details that were associated with continuous rod systems, such as the ATS system, where those rods at their base had anchorage details that looked something like this. Get to that slide. And they were terminated as a cast-in-place bolt in the slab. And it was common to have the anchorage cast in the concrete as opposed to below the concrete. And some of the reasons we'd want to keep that cast in, basically to protect against corrosion, against fire, vandalism, etc. See the details right there. See the anchor bolts stood off in the concrete, but again, cast in place into the concrete. So as calculations were done to try to get a better idea of what level of demand these sorts of installations could develop, we looked at a number of different scenarios, and here we have them here in this table. And those types of buildings included 3, 4, and 5-story structures over concrete podium slabs, like we mentioned earlier. The second column here, we have the description of the likely rod systems. So that includes what you see here, 3/4 inch mild steel with a strength of 58 KSI, all the way up to 1 1/4 inch rod with a strength of 125 KSI. These resulted in demands which we've labeled here as 1.2 times the nominal tensile strength. And there's a reason for this description that we're going to talk about in detail today. Now, 1.2 times the nominal tensile strength will result in those values that you see there in the third column. I think I've got a pointer right here. So anywhere, you can see the loads there. They're anywhere from 23 kips all the way up to 130 kips. Whereas if you calculate the nominal capacities for these installs at the edge and away from edge, as you see here in the last 2 columns, you'll see that while we may need to resist around 138 kips of demand, we're only calculating a capacity of about 51 kips. So we began to scratch our heads, realizing there was a bit of a disconnect between these two. So now that 138 kips that we just saw, as I'm sure we can all agree, it's a pretty large number. And we realize that people have been wondering for a long time, hey, is that actually a value that could be generated? That's something that could actually be generated during an event. Well, today there's only one test data point that we have in the world that offers a bit of reality to that. And this is from the 2009 NEESWood Capstone test project that took place in the world's largest shake table facility in Japan. This was a project spearheaded by Professor John Vanderlyn from Colorado State University, and it's a project that we participated in. The structure here is a 6-story light frame building and was tested under maximum considered earthquake level demand. So you can see all the people that had gathered there for the test. As a result of that testing, we had measurements on the Simpson ATS system, we had mentioned that earlier, And the continuous rod system, the ATS system, was actually built into the structure that was tested in the project. And we were able to get actual peak demands that were generated during this maximum considered level event. We have this value over here of 173 kips, obviously pretty high load there. Now this 173 kips was on 2 rods, as we had side-by-side shear walls in this condition. Now interestingly, if we go over here to the exterior, right, we see 123 kips of tension. Now this was peak demand. So that 123 kips is close to the 138 kips that we were talking about a few minutes ago.